All right, well, we're going to jump into the different types of reactions. And so we just looked at how to balance them, and now what we're going to do is kind of put them in various categories. And the first of these types we're going to look at are called precipitation reactions. And precipitation reactions are these reactions that form a precipitate, which is just a fancy word for an insoluble solid. Sometimes you'll see that word precipitate abbreviated PPT. Um, and this comes about from the reacting of two aqueous solutions. So for example, in this series of pictures here, we got a solution of potassium iodide. So that's in that beaker. And then we have a solution of lead nitrate. So let's write down the reaction or the reactants here for this. So we're going to take potassium iodide and lead nitrate. And they're both solutions, they're both aqueous solutions. And when they're mixed together, you can see that there is definitely something happen here. There's a reaction that's going on. This bright yellow solid that's formed is called a precipitate. And the identity of this solid is lead iodide. And so we would notate this by putting S there in those parentheses to indicate um, the state of matter of it. And what's happening here is there was this combination of ions. So potassium and iodide are soluble, lead nitrate was soluble, but in these precipitation reactions, the compounds kind of switch partners. The iodine goes over here with the lead, and the nitrate goes over here with the potassium. And the combination of lead with iodide forms this insoluble solid lead iodide. And what about the other part to this? Well, the other part would be potassium nitrate, and that stays dissolved in solution. And let's go ahead and balance it real quick. There. And one of the ways that we know that this yellow solid is lead iodide is through our solubility rules. Because if we look here, there's no lead ions in that left column, but there is iodide. And it's in the part of the table that says these ions are mostly soluble. But there is an exception for iodine, except when it's paired with lead. So when lead and iodide are paired together, it forms an insoluble salt. And we call that the precipitate. So let's do a couple examples of this, and we're going to predict if the mixture of two solutions will result in a precipitate. So let's start with potassium iodide again, and we'll react it with sodium chloride. And first of all, let's just predict the products. So again, in these precipitation reactions, all we're going to do is switch the ions up. So chloride's going to go over here with potassium, iodide's going to go over here with sodium, and let's just draw those formulas, KCl and sodium iodide, NaI. Now what we're going to do is look at our table here and see um, if either of these will form an insoluble precipitate. So K is here, potassium. Notice that's one of our ions there. And there are no exceptions to this being insoluble. So KCl is very soluble in water, so it will not precipitate. The same could be said for sodium iodide because sodium is, well, if something contains sodium, it is mostly soluble. And so there's no exceptions to that. And so that's aqueous. So this would form no precipitate. All right, let's look at one more. Let's look at the reaction of barium nitrate with sodium sulfate. So we're taking aqueous solutions of these. And again, we're just going to switch the ions. So the sulfate's going to go over here and replace the nitrate. The nitrate's going to go over here and now hang out with the sodium. So we'll end up with barium sulfate, and then we'll end up with sodium nitrate. So let's do a quick balance just to make sure everything is set. So maybe pause the video and try to balance it real quick. And then if you want to, take a look at the solubility table up there and see if you can predict if one or both of these products would form a precipitate. All right, so to quickly balance this, we need two sodiums. So I put that there. And that inadvertently also balances the nitrates because I have two nitrates on the left and now I have two on the right. So let's look at our table here and see. I'll just kind of erase these. Do we have anything with barium in the table? Barium doesn't show up. But if we looked at sulfate, it says there's sulfate. It's in the mostly soluble part of the table, but there is an exception if it's paired with barium. It becomes insoluble. So barium sulfate will definitely precipitate out. And how about sodium nitrate? Well, if you remember from the previous example, sodium, all compounds containing sodium cations, there's no exceptions, they're always soluble. So this will stay dissolved in water. All right, so as I said earlier in a previous lecture, I'm not going to make you memorize this table. I will always give it to you. You just need to know how to use it when it applies to these problems. And being able to predict if I mix two aqueous solutions together, will one combination of those ions form an insoluble precipitate? So to kind of round this out, and I'm still focusing kind of on precipitation reactions, there are different ways that we can write the equation for a lot of our reactions. This isn't limited to just precipitation reactions, but up until now, I haven't really put a label on the equations we've been drawing. And all the balanced equations we've been doing can be classified as molecular equations. And in a molecular equation, we write everything as compounds or elements if something's in their elemental form. And this type of equation is most useful for lab experiments because this will tell us like what compounds we need. What do we need to add together? And it gives us information about all of that. So like, for example, if we take an aqueous solution of silver nitrate and react it with sodium chloride, okay, I'm gonna do, I'm gonna switch the anions around. I'm gonna give the chlorine to silver and give the nitrate to sodium. Let's just predict something and see if um, one of these will form an insoluble precipitate. And so go back and take a look at the table, and you'll see that for silver chloride, all chlorides are soluble, except there's a few exceptions if it's paired with silver, mercury, or lead. So silver chloride is going to form a precipitate, and sodium nitrate, as we saw in another problem, will remain in an aqueous solution. Now, another way to write this reaction is to do what's called a complete ionic equation. And what this does is it writes all aqueous solutions as ions. And this kind of gives us the purpose of it is it gives us the most realistic picture of what's going on. And so I'm going to rewrite the molecular equation. And wherever I see an aqueous solution, I'm going to split it up into its ions. So that's Ag plus NO3 minus, and I'm still going to say aqueous. Because that's really, if I have a solution of silver nitrate, that's what's in the solution, is silver ions and nitrate ions. And then I'll have sodium cations in this solution and chloride ions as well. And then if it's not aqueous, I leave it as is. So the silver chloride is a solid precipitate. It doesn't exist as ions in solutions. It's a compound. But the sodium nitrate is dissolved in an aqueous solution, so I will write both of its ions. Now, finally, what we can do with that complete ionic equation is write what we call a net ionic equation. And the purpose of this is it kind of simplifies the complete ionic equation where we're going to get rid of spectator ions. And what do you think that means if I say a spectator ion? I mean, think of it like a spectator in a sport. If you're a spectator, are you participating in, let's say you're at a Laker game? No, if you're just watching the game. It's the same thing with ions. Spectator ions are not participating in the chemical reaction. And the way you find spectator ions is it's the same ion on the left and right side. And the benefit to this tells us exactly what is reacting. So let's go back to our complete ionic equation. And what we can do, much like a math problem, if you have a math equation, you can cancel things out that are exactly the same on the left and the right. We could do that with a net ionic equation. So notice how I have nitrate on the left here, and I have it on the right. I can cancel it out. Notice how I have sodium on the left, sodium cations, and sodium on the right. I can cancel that out. So my net ionic equation is just simply writing everything that's left. I have silver ions and chloride ions, and that makes the precipitate of silver chloride. And this is what we call our net ionic equation. We get rid of the spectator ions. They don't really matter. They're just floating around watching this game of silver ions reacting with chloride ions to make silver chloride. So let's work on a few problems to solidify this, and then that will be it for this series of videos. So here we have, all of these are already balanced molecular equations. We're just going to write the complete ionic and net ionic equations. So let's start here for A. So the the complete ionic for letter A, we're going to split this first aqueous solution into potassium ions. Now I want to start off right off the bat here with something important. Notice how many potassium ions we have here. Okay, I'm not going to do this, K2 plus. That doesn't exist. When this compound, K2C2O4, gets placed in water, it forms two potassium ions. And this ion here, this is known as oxalate. Don't have to know it. That's just part of this problem. So when we do the ions and they have a subscript, I'm going to put that subscript as a coefficient. Then I'll do the oxalate ion here. And now I'm going to break up barium hydroxide. So I have one barium, so barium 2 plus, How do I know barium is always plus two? It's in the second column. And notice here I have two hydroxides. So I'm not going to represent it like this. That's not good. That doesn't exist. I'm going to use a coefficient of 2. All right, and then I will do the ions for the other side. So the KOH is aqueous. Since there's a coefficient of 2, I'll keep that for the potassium. I'll keep that for the hydroxide. And then the final, or the last product is a solid, so I do not break that up. And that's my complete ionic equation. To get to my net ionic equation, I'm going to cross everything out that I see on the left and the right. So I have two potassiums here, two there. That's a spectator ion. I have two hydroxides here and two there. That's a spectator ion. Whatever is left is going to be part of my net ionic equation. So barium plus 2 plus the oxalate ion, C2O4, and that makes barium oxalate. Now, one of the ways that you can kind of like, I don't want to say game the system, but like if you identify what your precipitate is, and then you know what the ions those are made up of, then you can kind of already like shortcut your net ionic equation and say, well, here are my reactants, and it's going to make that as a product. So I'm just kind of going through these problems systematically and step by step. All right, so let's look at B. Again, everything that's aqueous, we're going to break up into its ions. So I'll start with lead. Here, lead is plus 2. And then notice in the balanced equation, or not necessarily balanced, but in this here, the nitrate, there's two of them. So I'm going to represent that with the coefficient here. Okay, now we have H2SO4. I have two hydrogens, so I'll have two H plus, and then one sulfate. Then the lead sulfate here will be our precipitate. I'm not going to break it up because it says solid. And then I'll break up the HNO3. So two H's here, two H plus, and two nitrates here. And there is my complete ionic equation. Now, to get to my net ionic equation, I'm going to cross out the things I see on the left and the right. So that's my two nitrates on the left and the right, two H pluses on the left and the right, and just going to indicate what is left. So that's lead plus 2 plus sulfate makes our lead sulfate precipitate. Now let's look at one more, letter C here. Okay, so now on our reactants here, our first reactant, calcium carbonate, it says a solid. That's fine. That's not, don't think of that as strange or anything like that. We just won't break it up because it says it's a solid. And the next reactant, though, H2SO4, is aqueous, so I will break that up. I have two hydrogen ions and one sulfate ion. All right, now I go to the products. I have calcium sulfate. It says solid, so I do not break that apart. The next product is CO2 gas. I'm not going to break that up. That's not even an ionic compound. So I definitely would not break that up into ions. And then the same thing with water. Water's not an ionic compound. So I don't break it up at all. And that's what my complete net ionic equation looks like. Now, for the net ionic equation, do I have anything that is the same on the left and the right? Well, my only ions here are H plus and sulfate. I don't have those on the product side. So my net ionic equation for this answer is the same as the complete ionic equation. And that's fine. There's no rules that say you can't have that. There's nothing to cancel out. So the two equations end up being exactly the same.